In the previous video, we learned about using the right hand rule 1 or the thumb rule or the right hand grip rule for finding out the connection between the current in a wire and the direction of magnetic field produced by that wire. Now, we have taken several examples in the previous video and learned about using the right hand thumb rule to get the direction of magnetic field. In this video, we will talk about how to calculate the value of the magnetic field. Now, in this example, we are calculating the value of the magnetic field created by a long, straight, current-carrying wire. As we can see in the top right picture, the current is going straight up, and using the right hand thumb rule, you're able to figure out that the field is making circular shape such that the curling fingers point out on the left side of the wire and they point in on the right side. So this is important, and typically coming out of the wire was shown as a direction with a dot inside a circle, and the direction going into the screen is shown as a cross. So this cross and dot denotes direction. This means outward direction from the screen, and this one denotes into the screen. Okay, having understood several examples of that, let's go here and you calculate the formula. Well, this is the formula for calculating the value of the magnetic field. This is an important formula. This tells us the magnitude of the magnetic field if you know the current I and the distance between the point at which you're calculating the field and the current wire. R as the shortest distance between the wire and the point at which you're calculating the field. Here's an example here. Well, in this formula, mu0 is referred to as permeability of free space. It is a constant whose value is given here in SI units. And at the bottom here, we do an example of calculating the current that produces a given magnetic field. So we're going to rearrange this equation in such a way that we can calculate current from the magnetic field. So that's what we arranged this equation here. And if we know the field, we can calculate the current required to produce the field at a given distance r. So take some time to see this problem. The field at some given point is given to be twice that of the strength of Earth. And so the Earth's magnetic field strength is typically 5 times 10 to the minus 5 Tesla. So the magnetic field in our problem now is twice that value, which is 10 times 10 to the minus 5, which is also this value here. And we are trying to calculate the current that produces this field at a distance of 5 centimeters from the wire. So essentially there's a wire carrying a current. Let's say the current is I, and we don't know what this current is, but then they have said at some point whose distance is 5 centimeters, what is the value of field? Well, they've given the value of field. Given is given. And using this given value of field, you have to calculate what current produces that field. And you can see that you substitute for R and substitute for the field and the permeability constant, and you get the current. So that's a simple example of calculating the current using this formula. So, but remember, this formula is useful only when you have a straight current carrying wire, and the formula contains 2 pi r, even though there is no circular wire here. We will see that this becomes a little important at a later point when we study field due to coils or loops. In this slide, we understand conceptual meaning of this formula that was presented earlier, and we're going to see how this formula can be plotted to understand the variation of magnetic field as the distance changes from the current carrying wire. As you can see, the magnetic field strength near the current carrying wire decreases with distance. It's because it's inversely proportional, and you can see that is shown in this picture. The magnetic field vector has a longer length here, which is at a closer distance, say R1, to the wire. Here the wire is carrying a current into the screen, shown by the cross here. So the wire is perpendicular to the screen and carrying current into the screen. That's how the field comes out to be in this direction, shown by the arrows. And the field value of B1, which is at a distance R1 from the wire, is of a longer length compared to field B2. The length of this vector B2 is smaller because this distance R2 is smaller or is larger compared to R1 because of this inversely proportional. So essentially, the further you are from the wire, the field is smaller or weaker compared to a point which is closer to the wire. And if you were to do a plot here of the distance R from the wire and the field strength, you will see that it shows you the 1/R relationship. This is typically the 1/R behavior. Essentially, it's telling you the magnetic field strength is inversely proportional to the distance from the wire. This example on this slide is an extension of calculation of magnetic field due to a straight wire. In this problem, we are calculating the total magnetic field produced by 2 wires at a point P, shown in this picture. The 2 wires carrying current, so we'll call this the wire 1, the one which is at the top, and wire 2, which is at the bottom. Wire 1 is carrying a current to the left, and wire 2 is carrying a current to the right, as you see in the picture. Both have the same value given by 5 amperes. Now, the distance between the point of observation P and the wire 1 is 8 centimeters. So this distance is the R required in the formula. We'll call it R1 because that's associated with wire 1. And that's about 0.08 meters. And this will be useful in calculating the field due to wire 1. And point P is at a distance of R2, which is twice this, so it's 0.16 meters, as you can see from the picture. This R2 is useful in calculating the field because of wire 2. First, the magnetic field at a point P is the vector sum of the fields at P due to each of the wires. It's a vector sum. That means we need to include the sign of the fields or the direction of the fields due to individual wires. You need to add them. Using the right hand rule, the thumb rule, at point P we find that the top wire 1 will produce a field which is into the screen. So the magnetic field due to top wire is into the screen. You can do that by using the right hand rule. Your thumb points in this into the left direction, and then you imagine that you're holding the wire, the top wire, and your curling fingers at point P will go into the screen. That's why it's a negative sign. It's into the screen. Similarly, due to the bottom wire, if you were to hold the bottom wire with the thumb pointing to the right, all your curling fingers at point P will be pointing towards you or out of the screen. That's why the field due to wire 2 happens to be out of the screen. And there is a sign associated with into and out of the screen. These are the sign conventions. Into the screen is typically referred to as negative sign, and out of the screen is given by a positive sign. So this will be useful for us when we try calculating the net field. So let us keep this in memory, that the out of field is positive and into field is negative. In this slide, we have calculated the field due to individual wires, and we're going to see what happens if we add them. Again, from the previous slide, we know that the field due to top wire is negative, the field due to the bottom wire is positive, and so B1 is due to the top wire. We can calculate using the formula for a straight wire, and it comes up with a negative sign here because it's into the screen. The formula is mu0I, current is given to be 5 amperes, and the distance is 0.08. That's what we noted earlier. So the field due to the top wire at point B comes out to be negative 1.25 times 10 to the minus 5 Tesla. Similarly, you can calculate the field due to the bottom wire at point P. Please note here the distance is 0.16 meters. And the current is same. You put in the value, you get this magnitude, but the sign comes out to be positive because the right hand rule showed us that the bottom wire has a field that points out of the screen at point P, and to get the total field you just do an addition, a vector addition. That would mean including the signs, you add them both, and this is your total field. And that's what the question is asking. So this is how you would be using the formula for field around a straight wire and calculating the total field because of more than one current carrying wires.